Good afternoon, classmates, Mr. Kubishin and Mr. Sempau. We are Francesc Gula, Ignacio Macià, and I, Joan Pros, and today we're going to present you the exercise 5.33 from the problem set of Unit 5. Okay, so to start with, we're going to read carefully this statement. We are asked to calculate the magnetic field created by an infinite sheet with a certain current density J at a distance Z from the sheet. Furthermore, this statement does explicitly ask for a demonstration using both Biot-Savart and Ampere's law. Finally, we're asked for the direction of the field in both sides of the sheet. Once we know what is our goal, we can start working on the assignment. If we take a look at the sheet, we can confirm that its field magnitude would be equivalent to an infinite amount of wires of infinite length. We've drawn this sketch to visualize it better. Indeed, if we were to cut the sheet longitudinally, as you can see, we could imagine lots of tiny current wires all flowing in the same direction. Note that we can express these little current flows by using the L, which is equivalent to the current density J multiplied by the length of this tiny segment, which we can call dx. It's also extremely crucial to set a reference frame and assign all three axes, in order to avoid confusions later on, because as you will see, it's sometimes difficult to express these 3D ideas in a presentation, so understanding the point of view of our approach is completely necessary. So, the z-axis points upwards to the point P in which we're asked to calculate the field. Then, the y-axis is the one in which the current flows. And finally, the x-axis cuts the currents perpendicularly. Take into account that the positive side of all three axes is located where the arrows are pointing in this diagram. Once all data has been organized and referenced correctly, we can proceed to develop all the calculations. The first method that we're required to use to solve this problem is Biot-Savart. As already mentioned, the infinite plane can be considered as many infinite wires together, so we need to calculate the field of each one of these wires. It's one of the first demonstrations done in this course, so we're not going to get into much detail. We have to use Biot-Savart's law and substitute these trigonometric equalities right here. The global result yields magnetic permeability multiplied by intensity and divided by 2 pi r. Once this demonstration is done, let's explain our sheet model more deeply. Okay, so we have drawn this kind of sketch in which we can see the currents directly pointing to us through the y-axis. So what you see here is the xz plane. We have defined a point P at a height z from the sheet, in which we are calculating the magnetic field. We can notice the direction of the field by using the right-hand rule, as you can see in these red and blue arrows right here. The current is flowing to us, and so our fingers would form a counterclockwise rotation.
Good morning, I'm Ignacio Macià, and I'm going to go over the steps needed to complete the exercise by using Biot-Savart. Once we have a clear view of the elements in this diagram, we take di, which is at a distance x from the projection of P on the plane, and we draw the corresponding field dB exerted on P, which is perpendicular to the trajectory line between di and the point, as it can be seen on the figure. If we draw another point P' at the same distance z but this time below the field, we see again dB at 90 degrees. It can be seen that each segment of the plane produces a perpendicular field at point P, and that the further the current is, the larger the alpha angle gets. If we take another di at the same distance from the projection, but to the other side, it should be noticed straight away that since the sheet is infinite, any di that we take will have an opposite and symmetric di with respect to the z projection. Therefore, the z component of the field cancels out, and the only existing field will be in the direction of the x-axis. Now, focusing only on the blue dB and using the Biot-Savart formula for an infinite wire, we have that dB equals the magnetic permeability times di over 2 pi r. Because of symmetry, we see that we are only interested on the x component of the field, and so we multiply the formula by the cosine of alpha. Also, the plane can be split in smaller current differentials, and so we say that di equals j dx. We call r the distance of the line drawn from di to point P, and so because of trigonometrical properties, we can say that r equals the square root of x squared plus z squared, and that the cosine of alpha equals z over r. In this case, however, we leave the cosine on the formula and instead substitute r by z over the cosine of alpha, as it will make the integration a lot easier later on. By doing these changes, we obtain the formula that dBx equals the magnetic permeability jdx over 2 pi z times the cosine squared of alpha. The next step is to apply the following change of variable, and after doing so, both the cosine squared and the z get cancelled out, obtaining that dBx equals the magnetic permeability times jdx over 2 pi. dBx gives us only the resulting field of a small part of the wire, and so in order to find the total field Bx, we must integrate. As the sheet is infinite, we know that alpha will go from minus pi over 2 to pi over 2. And then to integrate, all the constants go out, and we see it's a very trivial integration. After integrating, we obtain the final result, which is that the Bx equals the magnetic permeability times J over 2.
Good afternoon, I'm Francesc Goula, and now we're going to move to the second part of the exercise. It is basically doing the same problem but using the Ampere's law. The first thing we must do is define our coordinate system, which is on the top right of the slide. We need to mention that in this picture, the current of the infinite sheet is in the direction of the y-axis. Then we draw the Amperian closed loop. It's not really important how big it is, but it is really important to make it either parallel or perpendicular to the magnetic field at any point. It is also really important to draw it symmetrically around this 2D infinite sheet. Next thing we need to do is pick a direction which we have to integrate. So it defines the 4 red vectors in the image, dl, dl1, dl2, dl3, and dl4. Now we check that the magnetic field anywhere at the top points is in the direction minus x, and the magnetic field anywhere at the bottom or below this 2D infinite sheet points towards the right. It is very easy to check using the symmetric demonstration that we did before to determine that above the infinite sheet, the field will always point in the opposite direction of the x-axis. Besides, below the sheet, the field will always point in the direction of plus x. This is really important to solve the left-hand side of the Ampere's law. So let's go ahead and check this out. Applying Ampere's law for some loop, the line integral of the magnetic field around that loop is equal to the magnetic permeability times the current enclosed in that loop. We develop the Amperian loop, which we have broken down into 4 segments. So we are interested on integrating over B.dl over segment 1, segment 2, segment 3, and segment 4, basically through the entire closed loop. There are some simplifications as dl and the magnetic field are perpendicular for segments 2 and 4. For both cases, the scalar product is equal to 0, since the angle that B and dl form is equal to 90. So the cosine of 90 is 0. That means that now we're left only with 2 terms to solve. We have the integration of B dl over the top segment and B dl over the bottom segment. So B is going to have a particular magnitude over dl1. B is constant since there's no need for B to vary anywhere along this length, since all the points of dl1 and dl3 are at the same distance from the infinite sheet. So, since it is a constant, we can take it out of the integral. So we're left with the integral of dl1 and dl3 multiplied by the magnetic field. Then, both integrals are equal to L, and since it is a scalar product, we need to multiply it by the cosine of the angle they form. In both cases, is 0. Now we have to evaluate the right-hand side of the Ampere's law. How much current is actually enclosed in that loop? Well, for that one, we use the fact that we know the current density J, that is how many amperes we have per unit length. Then, the current enclosed is equal to the integral of J multiplied by dx, which happens to be J per L. L is the long side of the Ampere's closed loop. Then, we're left with this equation, and if we isolate B, we obtain the result. That is, the magnetic field is equal to magnetic permeability times J over 2. We hope that our explanation was clear, and if you have any questions, we will be glad to answer them. Thanks.